Okay, good afternoon, everybody. This is Michael McClellan. It's great to see you all again. Thank you for attending another Levine Electronics and Electric COVID-19 webinar. Today we've got a very special guest. Josh Brandenburg is with CE Power, and he has spent a great deal of time on arc flash calculations, and he's going to share with you today for the next hour how to perform these arc flash calculations per IEEE 1584. You are on a webinar, so your phones are muted, but you can ask questions. There's a question box to the right in your toolbox. You'll also see some handouts to the right that you can download and review later. And so we hope you enjoy this. And at this point, I'm going to turn it over to Josh.
Hey, thanks, Mike. Can everyone see my screen right now?
It's looking good, Josh.
Okay, then Alex, do you want to kick it off and I'll slide through?
Yeah, absolutely. Good afternoon, everybody. My name is Alex Aguiar. I am the marketing specialist for CE Power, and I want to welcome everybody to our webinar. Josh Brandenburg will be giving a presentation on the IEEE 1584 updates to arc flash calculations, and we will also hopefully have Tony Sargent join us as well to talk about a lot of the mitigation techniques that we are able to provide for those experiencing high incident energy rates. I'll go to the next slide. And as I mentioned, what we'll be going over today is a brief introduction into arc flash basics and applicable standards. After that, Josh will dive into the 2018 updates to the IEEE 1584 standard guide for performing arc flash hazard calculations, including some case studies comparing real world results from the 2018 study and comparing that to the last time IEEE was updated in 2002. And as I mentioned, we will also be talking about some arc flash mitigation, solutions that CE Power is able to provide to your equipment. Just a little bit of overview of CE Power here. CE Power is part of a larger holding company called Qualys Power Services. We partnered with Power Grid Engineering in 2018 to bring a variety of end-to-end solutions to our customer base in both the transmission, distribution, and generation fields. So the Qualys Power Services was created to join CE Power and Power Grid Engineering. As you can see on the screen, we offer a myriad of different services available to any electrical system. Go to the next slide. We also have geographic coverage to fit your needs. As you can see on the slides, we have many locations from Maine all the way down to Florida, all the way west to Kansas and northern Minnesota. So we are essentially a half power system will travel type business. I'll go to the next one. And just a quick brief overview of CE Power. CE Power is a NETA accredited electrical and testing organization. We test to the highest standards. We also feature a life extension group for preserving the life of existing equipment, our engineering services, the PES team, and our PEG group, which focuses on large greenfield and brownfield type substation projects. And we serve the utility, industrial, and commercial markets primarily. So without further ado, I will kick it over to Josh to start talking about our arc flash basics.
Yeah, thanks, Alex. The primary topics today are going to be the 1584 updates. They had a new 2018 model, and so that's the first major topic, and then we'll get to the arc flash mitigation stuff. But I've got two slides here to kind of do a quick cold start on what is arc flash. So that's the thermal energy impressed on the surface of specified working distance. IEEE 1584 says that the incident energy that will cause a just curable burn is 1.2 calories. That's the second degree burn cutoff. Interestingly, 8 calories is kind of the cutoff for a third degree burn. And so when we do these studies, a lot of times we see calorie or ratings above that 8 calorie threshold. And so this stuff can be pretty dangerous, and that's at a working distance typically of 18 inches. So what does that mean about your hands when you've got those in there? So you should probably be wearing gloves because the value at that close of a distance is much higher. And so these events, when they happen, they can be pretty significant, and they happen 5 to 10 times a day in the U.S. So that's enough. It's a significant enough concern, and it happens frequently enough that you have quite a bit of regulation on how we approach this and how we need to make sure that we're keeping our workers or employees safe should they need to be exposed to this. And so OSHA 1910 requires that employers perform a PPE hazard assessment to determine what type of PPE someone would have to wear to work on electrical equipment. The NEC has requirements that all of the electrical equipment have a label on it signifying or indicating an arc flash hazard. NFPA 70E, similarly to OSHA, requires that a risk hazard assessment be performed prior to working on equipment. And 70E also offers some guidelines on how you might achieve that. We have to do an assessment. How do we do that? So they offer some methods. They talk about the Lee method, which is a long time ago what was used. Maybe not the best method because it's theoretical. Similarly, we have the maximum power method, which they also mentioned. Again, theoretical, maybe gives too high results. They also have some tables in there that they say you can use. If you've got this type of equipment, you have to wear this type of clothing to work on this equipment. The problem with those tables and the problem with the other analysis methods is, well, specifically with the tables, they make assumptions about clearing times and fault current levels. And the only really good way to know that is by modeling it in a computer analysis software like SKM or ETAP or EasyPower. And once you do that, you might as well use the best method, which is 1584. And the reason that one's probably a little better than the others is because unlike the others that were theoretical, this one's based on empirical test data. So they simulated arc flash events and measured the calorie readings for those events, and they looked at different variables to see how those affected the calculation. So that was true in 2002. It was also true in 2018. So why did they do the change? Well, they noticed the 2002 one maybe wasn't perfect. It was a good first effort, right? They had 300 test points. But maybe that wasn't enough. Maybe they didn't look at the full spectrum, the full range of voltage and fault currents and have enough data points on that. They had some assumptions that maybe weren't the best to have in that model, specifically the low volt transformer exception. That's kind of a big change from the 2002 to the 2018. That went away in the 2018 one. It's no longer in there. It was replaced with something that's going to be one of the major talking points today. And maybe they didn't look at all of the parameters that they needed to. Things like enclosure size and electrode configuration weren't strictly considered in the 2002 model. Turns out those might have a pretty substantial impact on the calculations. 2018 kind of resolved a lot of those things. They had much more robust testing. From 300 test points to over 1,800. More parameters, they considered things like enclosure size, electrode configuration. They also have some application guidance because some of those new parameters can be a little bit confusing to understand or to understand how they apply to the way you need to do your calculations. So they've got some stuff in the annexes that offers some guidance on what you should look at. And they also have completely new equations that they used to do their calculations. And so I've actually got, this is the actual equation that is being calculated. And so I just have this on the screen so that we can, appreciate having the computer analysis do this for us, because that would not be fun to solve by hand. So I don't have the 2002 one up here, but this takes up the whole screen. The 2002 one took up maybe a quarter of the screen. So it's a lot more robust and a lot harder to solve by hand. So with that, we'll kind of go into all the parameters. We'll throw all of them up here and look at how they changed, and then we'll dive in to a few key ones. And so really the focus of this update is going to be talking about those ones that are highlighted in yellow, but we'll go through all of them and talk about if they change and why. So the first one is the voltage range. That didn't change between the two models, still 208 volts, 15 kV. Frequency didn't change, still 50, 60 hertz. Fault type didn't change either, so it's still three-phase faults. That's an important note because there's still no official standard for single-phase equipment, although the 2018 standard does offer some verbiage about what you can do for single-phase equipment, and it basically says if you can figure out the single line to ground current, fault current, and you should be able to use that in these three-phase equations and get a conservatively high value. And so when you do that analysis in the software, that's basically what that's doing. Voltage fault current range changed a little, but not really. Still the same ranges. They looked at it at voltages now, but not a big change. Number of tests, you know, as we've already talked about, big increase from around 300 to over 1,800. Electrode configurations. We'll talk a lot about this one, but in the 2002, they looked at 2, now they've looked at 5. Enclosure dimensions, they tested these in commonly available sizes in 2002. Now they've kind of looked at this as a variable. So we'll look at how considering this as a variable for how big the enclosures are and see how that affects these calculations as well. Arcing current variation, we used to be 85% for low voltage systems. Now it's variable upon the voltage level. It turns out that it's still around 85% for those low voltage systems, but it's variable now, not a major change. Bus gap, they broadened that range, but most of the equipment that we consider has a bus gap that falls within both ranges. Working distance wasn't specified previously. Now it is, it's 12 inches or larger. Again, not maybe a huge deal because the typical working distances that we consider are already greater than that. Typically, we look at 18 inches or greater. System grounding was looked at in the 2002 model. They didn't look at that in the 2018 model. Their basis for that was that the calculations were based on a more stable arc, and so they didn't need to consider that. So now I've got down here the low volt transformer exception that existed in the old model that does not exist in the 2018 model. We'll talk more about that on the next slide, actually. And then to finish out the list, still nothing on single phase, it's still out of scope of the standard. DC equipment, still out of scope of the standard. And the 2-second rule as a maximum clearing time is still in there. And so with that, we'll move to the first major topic of the presentation, which is the low volt transformer exception. So this has gone away. And so I'm going to read the verbiage from the 2002 and the 2018 and we'll compare. So 2002 said the arc flash hazard need only be considered for large 208 volt systems. Systems fed by transformers smaller than 125 kVA should not be a concern. And so this was great because what this meant is that you didn't have to model individual components down below a 125 kVA transformer. So this statement doesn't exist in 2018. What 2018 says is this: sustainable arcs are possible, but less likely in three-phase systems operating at 240 volt nominal or less with an available short circuit current less than 2000 amps. And so what you'll notice about that 2018 verbiage is that there's no mention of a transformer size at all. There's a mention of a fault current value. And so now the question is, okay, well, how do I transpose that into transformer numbers? It turns out that's pretty hard to do. It depends on the kVA size, and it also depends on the percent impedance and other system variables. So there's a good chance that 15 kVA transformers, you're really not going to be able to get a fault current out of those transformers greater than 2000 amps. So it looks like those probably still don't need to be considered. 30 kVA, it depends. Sometimes a lot of times it won't be a concern, sometimes it will be. And then when you start getting above that, you're probably going to have to model it and analyze that individually to see how the results change. And so naturally, the commercial implication here is that this is a scope increase, whereas before we could get away, so to speak, with not modeling transformers 125 kVA or below. Now maybe that number's gone down to 30 kVA or so. So now let's look at here on the next slide how these numbers change when we take this exception out. And I think this is an interesting insight as well. So the key thing to take from this table is that column there on the far right. The red indicates that that is an increase in incident energy from the 2002 to the 2018 standard for these formerly small transformers, right? And so we can see that when we remove this exception, it's increasing the incident energy, sometimes by quite a bit. Sometimes it's a insignificant change, less than a calorie, but there's definitely some instances there when you're looking at the column on the right where it's gone up by 8 calories, 12 calories. So now instead of that 1.2 calorie value, right, the cutoff for a second-degree burn, some of these pieces of equipment are now seeing incident energy values above 12 calories. So it's a pretty significant jump. So this is definitely one of the biggest takeaways from the changes from the 2002 to the 2018 standard. So with that, I'll move on to the second major topic, which is the enclosure correction factor. And I think this one conceptually makes sense, makes good sense. When we have a smaller enclosure, the explosion or blast can't spread out to the sides as much. So that energy gets directed towards the opening, towards the worker. And so as you can imagine, that means that the incident energy calculation is also higher. Conversely, with a larger enclosure, the blast can spread out more, and so it's less focused, and that leads to a lower incident energy. Open air conditions, so that's referring to the electrode configuration, which we'll talk about next. Those tend to look like a larger enclosure, right? Because there's room for that blast to spread out. It's less focused. And so what does this variable get us? Well, when we look at the larger enclosures, it can reduce this incident energy calculation by up to around 20%. And so let's look at this graphically now. Easy Power has a really good visual of what this is really doing behind the scenes. And so we can see there on the left, that's that minimum enclosure size, 20 by 20 inches. Anything smaller than that still has that correction factor of 100%. And then as we get a larger and larger enclosure, up to the 49 by 49 inch point, it can be reduced by up to 20%. And so I think conceptually that one makes a little bit of sense. What does this mean for the user, people doing the studies? How do we need to think about this and control for this when we do our data collection or do our analysis? Well, the 2018 model has some standard enclosure sizes that they use for testing. And so the good news here is that in the software, if you correctly select the equipment type, whether it be an MCC or switchgear or panel board, the software is going to default it to the values that you see there in the table. And those tend to be good. So while this can be a big change to the values, it's kind of latent to the user. As long as you're selecting the equipment type correctly, this correction factor should be being applied properly. Now, obviously, if you have a piece of equipment that you observe out in the field and you think that the size is way off, you can also manually adjust that. So now we'll move on to the final major topic of the 1584 update, which is the electrode configuration. And I think this is the biggest one, but it's also maybe conceptually the most difficult to understand. So we'll give it a shot here. 2002, they considered two configurations. That's what you're seeing there on the screen. arc in a box on the left, and an arc in open air there on the right. In 2018, they considered 5. And so I'll read these off left to right. VCB, which is what they used in 2002, that's vertical conductors in a box. They also consider VCBB, which is vertical conductors in a box in an insulating barrier. Right? And so that's, you can see there, the conductors are kind of butted up against the bottom of the enclosure. That's the barrier. Figure 3 is vertical and open air, right? And so that's what they considered in 2002 as well. They also looked at some horizontal configurations. And so that's figure 4 and figure 5, horizontal conductors in a box, horizontal and open air. And so again, conceptually, as you might expect, those conductors pointed directly out towards the worker, as seen in the horizontal configurations. Those tend to give higher incident energy values. And we'll look at that more later on in these slides. So now that we've talked about what they are, let's look at some of them, what they might look like in real life. And now we'll start to see some of the difficulties with considering this in the analysis. So the first 2 pictures there on the left, those are straight from the 1584 standard. And we can see that's the same enclosure. And depending on where your fault occurs, you could have a different electrode configuration. So if you have a fault in the region shown in the picture on the left, that would be VCB. If you have a fault in the region showed in the picture in the middle, well, that's VCBB. And so we've got the same enclosure, and depending on where a fault occurs, we have 2 different types of electrode configurations that we need to consider. So what do? This is the hard part of considering these correctly. Some of the softwares, if you're using the latest versions, they have check boxes that you can check so that you consider both. And if you're working on the most up-to-date softwares, that's your best bet. If you can only look at one, it turns out that VCBB, 2 Bs, tends to be worse than VCB, but not always. So if you can only consider one, you should probably consider the one with the 2 Bs. And in MCCs, it's not realistic to consider HCB, which we'll look at now. So here's some pictures of what that horizontal, that more dangerous configuration looks like in the real world. So these are you'll typically see this set up in switchgear with draw out circuit breakers. That is typically where this hazard exists. And that's when you need to adjust that accordingly. HCB, as we're going to see here in a bit, is always worse than the vertical configurations. So if you have this is what you should be considering. And then in the picture on the right, we can see how this problem can even further be complicated, right? Because we've got a switchboard lineup where we've got a main breaker, that's a draw out circuit breaker. So that's got, the HCB configuration. But we look there on the section on the right, those voltage case circuit breakers, those are vertical configuration, right? VCB or VCBB. So how do you want to handle that when you're doing your analysis in your software? And so that's the complicated part. You could break them into 2 buses and consider a calculation for the main compartment and a calculation for the feeder compartments. But then you have to ensure things like electrical isolation, and you can see how that can complicate the analysis. But it's something to be aware of, and these are the types of things that engineers are thinking about when they're performing this work based on the new standard. And so I do have one more set of pictures. This one's a little bit easier. These are the open air condition, vertical open air on the left and horizontal open air on the right. These are a little bit easier to pick out, I think. So now we're going to look at a series of graphs that are all going to look, take this form. The important thing to remember on these graphs is that the green curve there, that is the 2002 standard. The gray curve is the VCBB configuration. The red curve is the VCB configuration, and the blue curve is the horizontal configuration, right? And so what we're going to see here is that blue curve tends to be higher than the other ones. So let's look at this first one, though. This is bolted fault current versus arcing current. So you can see that All the 2018 versions tend to be a little bit higher than the 2002 version. So your initial reaction might be, oh, well, that means that all the incident energy values are going to be higher in the new standard. What we're going to find is that that's not the case, because this isn't accounting for clearing time. And so we'll talk about that later. What happens when you look at this against a protected device? We're going to look at that. So let's look next at voltage fault current against the incident energy values, right? And let's hold our clearing time constant at 100 milliseconds. So now we can start to see some separation. Right? We see the old 2002 standard in green. Well, now it looks like the VCBB can be a lot higher than the green curve, and it looks like the horizontal configuration is always a lot higher. But again, maybe this isn't the best thing to do, is to hold that clearing time constant, because we know that breakers and fuses, well, they can have different clearing times depending upon what type of fault current you're looking at. So now let's do that. Let's put a protected device in the circuit and look at what these incident energy values look like when we have a protected device in there. So now we're not holding the clearing time constant. We're looking at this with a 600 amp Busman fuse. So when we stick a fuse into this analysis, this is the response that we get. And so now is when we start to get some really interesting insights about the changes from 2002 to 2018. We can see that the gray and the red curves, those are the vertical configurations, the things that you'll see in panel boards and MCCs and other equipment. It looks like it's less than the 2002 standard. Obviously, you can see the blue curve, the horizontal configuration tends to be much higher than the green curve or the old 2002 standard. So that's things like switchgear. So now let's look at, let's put a breaker in there instead of a fuse. We can see similar results. Horizontal still tends to be worse. And then the gray and the red curves, the vertical configurations for the new standard tend to be lower than the old standard, right? So again, switchgear higher than the old standard, and then panel boards, MCCs, other equipment tends to be lower than the old standard. And so one last curve that looks like this, let's put a big 3000 amp square D breaker in the circuit and see how it behaves. And now we can see some more separation in these, looking at like an LSI functionality of a breaker. We still see that the horizontal configuration still a lot higher than the old standard typically. But now, interestingly, we can see some times where the gray curve is higher than the green curve, right? And so this is where those panel boards or MCCs might actually be higher than the old standard as well. And interesting, around the 40,000 amp fault current range, we can see an occasion where the red curve goes above the gray curve. So again, referring back to previous conversation, the gray curve tends to be higher than the red curve, but not always. And this graph here kind of demonstrates that. So those are the visuals for the electrode configuration. Now let's look at some, high system level stuff. So here are some incident energy values for a 4160 commercial building system. We can see, again, in the far right column, the red means it's gone up by that much, and the green means it's gone down by that much. We can see that there's not a whole lot of change between the two models. And so the focus of this presentation has been with low volt systems, and this is kind of why. These are anecdotal data points, but speaking generally, there was far more sensitivity with the low volt results than the medium voltage results. That those didn't change as much as the low voltage calculations, and this kind of backs that up. So now let's look at a low volt system. Let's look at a 480 volt system. We see a lot of green there. So again, this backs up the curves we were looking at previously. Sometimes we're seeing substantial drops. If you look in the right column, some of those have gone down by 30 or more calories. And the reason that's happening is because of that very first graph we looked at, showing that the arcing current has gone up And so what that has done is caused the clearing time to go way, way, way down from 2 seconds down to 50 milliseconds. And so that's why that calculation is dropping by that much. And we do see a few instances where it has gone up. And as we saw in the graphs, there are definitely circumstances where it can go up. I don't see, the switchgear is probably the biggest concern with the results about being higher than. Let's look at 208 volt systems. You can see a similar behavior, but now there's more red, and a lot of this has to do with that low volt transformer exception. When we take that out, as we talked about with the very first item, when we remove that exception, we see a lot higher values. And so, this is a subset of a system, but this kind of backs up that idea that when we remove that exception, you can get higher values. So, where does that leave us? Well, it's been a complicated change from the 2002 to the 2018 standard. We can't categorically say something like, well, the 2002 is always higher than 2018, or the 2018 is always higher than the 2002. We can't, accurately make a statement like that. It depends. The universal engineering answer, it depends on, what you're looking at in your system. And so the low voltage transformer exception causes, or the removal of that exception causes these values to go up. Electrode configuration can cause them to go up. It can cause them to go way down. And so I think this, kind of reiterates the importance of using this new standard. It is far more robust. There's no, requirement that you do a study update today because of this change, but you can wait for your typical 5-year update to incorporate this. But I think there's there's evidence shown here that those values have definitely changed sometimes for the good, a lot of times for the good, but there's instances where they've gone up higher too. Things to be conscious of is that allow for some more data collection time, because we don't have that transformer exception anymore. We have to go and get that data now. And we also have to think more strategically and do more planning for things like electrode configuration. So that can add to some analysis time. And so that is the material that I have prepared for the 1584 update. I think now is the time where we'll take a poll question. And Mike, I'm kind of looking to you for guidance about how you want to do that. Do I just need to ask that question here verbally, or? I can go ahead and do that. And so the poll question is, what are some of the major changes from the 2002 standard to the 2018 standard? That's the poll question. And this is not for a grade.
Everybody's working on that. Josh, we have a couple other questions. Here's one. Based on the NFPA, we have to still use 1584-2018, or is it still optional?
Yeah, good question. There's been no change to OSHA or NFPA 70E saying that you have to use the standard. As I mentioned at the very beginning, in order to use some of the other methods like the table method, you need to know things like the clearing times and the fault current levels. And so in order to know those, a lot of times you have to build it in a modeling software anyway. And so at that point, it becomes reasonably easy or much more practical to actually use this analysis method. But there is, no strict regulatory requirement to use it.
Okay, here's another. This is a good question. Is HCB and VCB configuration only considered at the termination point to the breakers, or anywhere inside the equipment?
Anywhere
Consider
inside
that we have.
Sorry, go ahead. That's a good question.
Consider we have large switchboards with many sections.
Yeah, and so that's kind of, you know, what I was trying to get at on that slide, looking at some of the equipment. When you have multiple sections, it can be complicated. But the answer is anywhere inside the equipment enclosure. It's not just at the termination points. Typically, what you see for, you know, switchboards and panel boards, MCCs, you're going to have one of two considerations, which will be the VCB or VCBB, and that's why it's always best to look at both. And so updated versions of the modeling analysis softwares have the capability to simulate both or all three, but you probably don't need to consider horizontal everywhere. That's more of a consideration for, you know, draw out circuit breakers, things like that. I think that's maybe enough time. So, you know, if there's no more questions at this point, we'll be taking questions again at the end of the presentation. But otherwise, I want to kick it over to Tony. And Tony's going to talk more about the arc flash mitigation. So, Tony, if you want to jump in, I'll turn it over to you.
Yes, thanks, Josh. Great job covering that. Michael, did you flip it over to my screen?
No, let me. You need to press the button that says share screen. I can also, let's see, I need to make you the presenter. Let's see. Okay, so now you're the presenter.
Okay, so you guys can see my screen now?
There's still the poll up, so give that 10 more seconds, and then I will close that. And then I'm sure we will see your screen again. Okay, so I see a screen that says mitigation techniques, decrease time, decrease distance.
Perfect, thank you. Josh, thanks again for going through that. So I'm going to walk through some of the arc flash mitigation techniques that we've worked with some of our clients on. And there's really four, you know, a couple points that I'm going to go through. I guess first and foremost, you know, to get to this point where you identify that you have an arc flash hazard in your facility, it goes without saying that obviously you want to get a study completed. I'm hoping that most on this call have already. Michael, I got a. You still have my screen? I'm sorry.
I can see it, Tony.
Okay, I'm sorry. I got a prompt. So anyway, goes without saying, obviously, you know, you want to have a study done or updated. As far as mitigation goes, we can go through older studies to identify some of those issues and hopefully some of those solutions. So really, I'm going to focus a majority of my time talking about decreasing time. In other words, how long it takes for the circuit to open in an arc flash event, and increasing distance, so getting workers away from the hazardous areas or hazardous equipment. Real quick, you can see on the screen there's a load break switch on the left. Very common for us to go into application and put vacuum circuit breakers. So obviously, you know, a vacuum breaker is going to open much quicker than a fuse. So you're, again, decreasing time of the circuit opening. Increasing distance, we've got on the bottom there, you can see infrared window on a 5 kV motor starter. So again, eliminating the need to open the panel, and you can get your IR gun right there and take a look at the terminations. Lastly, we're going to cover a little bit on prevention. We're showing some high resistance ground. And one area that we're not going to cover, because most of the times it's not practical solution, is reducing the current. So, you know, there are ways to do that with current limiting fuses or with reactors where, you know, a lot of times it's, you know, big equipment, or as far as coordination goes, it's very difficult to apply those. So we'll get into decreasing time. We're going to cover lower instantaneous settings, both on low voltage and medium voltage circuits, trip unit upgrades for low voltage breakers, relay upgrades, differential protection, and then sacrificial components. So as far as decreasing time, a lot of the newer power circuit breakers out there today have, call them ARMs, call them quick switch, call them quick trip. There's a lot of different language out there. So not only can you buy those options on your trip units for newer low voltage power circuit breakers, but you can also use, in this case, AC Pro for a older air circuit breaker. So maybe you have dash pots, maybe you have an older solid state. AC Pro makes a product where you can actually put a quick trip device on an older circuit breaker. And the thought is to, in a maintenance mode, when you have either, work going on downstream, you're changing settings on a breaker, you have an outage going on, whatever the case may be, you could put the circuit in a maintenance mode. Obviously, you're going to be sacrificing coordination, but you're going to be opening that circuit a lot quicker in instantaneous mode. So again, decreasing the time to open that circuit in the event of an issue. Along with that, they also make an option for ZSI, and really ZSI has been around for a long time, zone selective interlocking, where you're opening the circuit closer to the fault. Twisted pair, that's, essentially the breakers are talking to each other and making sure that you're opening that circuit a lot faster, not waiting for a main breaker to open up. On the medium voltage side, a lot of options with relays these days. On the right, we're showing multi-lin. They have a lot of great options with the 850, the 8 series. And again, you could put group settings in where if you do want to open up that circuit faster in a maintenance type activity, you could do so by literally sending a signal into the relay and changing that coordination curve. There are options for optical light detection, so increasing current and a optical hazard. So in other words, bright light typically would emit in the event of an arc flash, either in the bus compartment or the cable compartment, is going to trip in milliseconds. So again, if there's work going on in the equipment, or if there is an equipment fault when it's running, lowering or opening that circuit in milliseconds is going to do two things. One is going to, if there are workers in and around that equipment, it's going to open up faster and hopefully prevent molten copper, panel discharge, whatever the case may be, and also is going to limit the damage done to the equipment that's being affected. Differential protection, again, it's been around forever. Current in, current out. These days with some of the multi-lin products, you can absolutely open that circuit very, very fast. So it's utilized a lot for, not only bus, but for transformer protection. So in the event of some kind of failure, phase to phase, phase to ground, you're going to be able to open up that differential a lot faster and not only hopefully save lives, but save the equipment as well. Sacrificial components. So in this solution, we're talking about ABB makes a product called the UFIS device, ultra fast earthing switch. It's a combination of devices consisting of electronic device, corresponding primary switching element. So what are we doing here? Essentially, what you're doing is you're taking an uncontrolled fault and making a controlled and predictable three-phase fault. So on the left-hand side of the picture, we're showing this application. I believe that's a 15 kV load break switch. So essentially what you're doing is you're creating a bolted fault in a controlled environment. And we've had situations with customers where we're going from, call it 75, 100 cals down to a class 1 type or a level 1 type hazard. So, obviously PPE requirements are decreased dramatically, and it creates a much safer work environment, and as well as reducing equipment hazard. So we're going to shift gears to increasing distance. So we're going to go through a few things here. Again, this technology has been around for a while, but very effective. Remote racking for both low voltage and medium voltage circuits and switchgear, remote operation, and removal of personnel from the hazardous areas. So these are, pretty simple, pretty cost-effective means to protect personnel. Remote racking is a real simple one. So we're taking, some kind of device, whether it be a rack, as you see on the left, that rolls up to the switchgear, or on the right. This is a pendant mounted, so it's got shoulder bolts on the switchgear, mounts on the gear itself, and you tether away 25, 50, 100 feet away, and you can actually rack the breaker in, or the contactor in and off the bus from a remote location, therefore getting your personnel away from the switchgear. Remote operator, same concept, where you actually mount the device on the switchgear, typically on the door, and there's a mechanical actuator that will actually operate the circuit breaker, much like personnel's hand. So again, you're getting the workers away from the hazard and letting the equipment do the work. Mimic panels, again, this is technology that's been around for years and years and years. Getting the relays and the breaker control switches, and even on the left there, you can see an installation we did for a pharmaceutical company. You're getting the test switches away from the switchgear, so we can actually test the relays, test the circuit, open and close the circuit breaker, adjust settings, with control wiring going into the switchgear or the breaker cell, and then away from the switchgear, so that when you're doing that activity, you're away from the circuit breaker and the bus. Time delay switches, same kind of concept. I had a video on here, but it wasn't working. But essentially, what you're doing is there's a little button on the left. So rather than the breaker control switch being in front where you're opening and closing, you're actually hitting a time delay button, and there's a timer in that device that will actually actuate the breaker control switch, 20 seconds, 30 seconds, whatever the setting you put in there, with a dip switch. So your operation folks can safely push the button, walk away from the switch gear, and the circuit works. Infrared windows, again, simple, easy method to get personnel away from switchgear, not opening panels. So literally opening that device that is mounted on the panel rather than opening up the panel itself, and putting your gun there and doing your infrared scans. This particular brand has a clear polymer version, so that you can actually do visual inspections as well. So if you're looking at any kind of bus connections that are of concern, or cable terminations, you can safely do so without having to remove the panel. Not only are you exposing yourself to the bus and the cable, but you have the risk of potentially dropping the panel into the switchgear, which does happen on occasion. Remote oil sample ports, again, for transformers, very simple, inexpensive solution, where rather than opening up that cabinet and exposing yourself to live parts to take the oil sample and the cable, you can simply go to the side of it and open up the port and not have to get exposed to live parts and cable. As far as prevention goes, probably 95% of the United States is, designed and built around solidly grounded systems, except those of you out there that, in the paper industry, pharmaceutical industry, that go with high resistance grounding. But essentially what that's doing is limiting the line to ground fault. It's also, reducing shock hazard. So when going from solidly grounded to high resistant grounding, there's some process improvements there, reliability improvements, and there's also some essentially some arc flash mitigation techniques as well. So it's pretty involved process to make that conversion, but we have done some for clients, and there's big benefit there. Michael, I don't know what my poll question is. Maybe someone else does, or we can move on. It's your choice, Michael.
So there's a poll question up right now that folks are answering, and it is, do you have any equipment on site that is category dangerous?
Yes. The go-to webinar is a little smarter than me. I like it though. So I'm going to buzz through this real quick, and hopefully we'll leave some time for questions. But little case study. This happens to be a large commercial facility in the Northeast. Very typical of what we run into around the country. 15 kV incoming from the utility, about 50 MVA a load. Distribution voltages of not only 12 kV, but 480, 208, 120. So lighting, motors, pumps, a large HVAC load. Very, very typical commercial building. Build out from the 30s all the way up to present. In fact, we're doing work there today. 26 substations in total, and a mixed bag of manufacturers: GE, Allis-Chalmers, Westinghouse, basically everything you can think of. Most of the equipment in the basement, not terribly accessible, with risers going up to the building, and as you can imagine, cable everywhere, built out over the years. So kind of step one. So we did the short circuit coordination arc flash study. Thousands of devices, and really what we found was, of the 26 substations, majority of them were 25 to 100 calories as far as arc flash hazard. As far as first phase, typically when we're done with that, we'll pluck off some of the easy things where you change potentially some relay settings, maybe change some fuses on a short outage. Replace some circuit breakers or some fuses that are over dutied. Really go for that low hanging fruit first to improve what you can and see where you left. Really step two, moving into that, is in conjunction with doing that, making those changing settings, or those setting changes, we're doing maintenance on equipment as well. So we're really getting equipment back up to snuff. Not uncommon for us to find equipment that the breaker's been closed for 20 years, never been operated, really needs some good old maintenance, some lubrication on the breaker and the mech. So really that's a big recommendation for us. And then along with that, prior to the outage, possibly doing some IR scanning if possible. Moving on from that, those substations that we can't make adequate changes to, because it's a little bit more intrusive. In this case, we actually put in the REA and the UFIS device that I showed earlier, where we went from, on the 12 substations, went from anywhere from 25 to 100 cals down to 4 calories. So big improvement there from an arc flash perspective. Along with that, while we're doing that work, we upgraded, circuit breakers from, old dash pots to breakers that have dual settings. So, for those downstream MCCs, downstream switchboards, we're able to address some of that, those flash hazards there as well. During the same outage, put in IR windows. So not only are we, making downstream and that equipment safer, but we're also, while as a go forward means, we're putting infrared windows in so that we're not having to remove panels for their personnel to go in. So big savings there as well. So I guess in conclusion, and this is a work in progress. Trust me, this wasn't done overnight. We're actually still actively doing work at this facility and improving their arc flash perspective and the reliability. But in almost all cases, we're able to go from 20, like I said, 25 to over 100 cals to majority of the facility under 8 calories, all the way down to the motors. So big improvement from incoming utility all the way down. I think that's all I had. I don't know if Michael, if you had any questions pop in that perhaps we can answer, or if that's all you had on the agenda.
I think we answered all of the questions. There is a one remaining poll question that has just popped up for our folks, and that is, when was the last time you performed an arc flash study at your facility? And you can answer within 6 months, a year ago, 2 years ago, and 4 years ago. Tony, do you have a feel for how often folks should be performing an arc flash study?
Yeah, good question. So I believe there's some OSHA regulations that require every 5 years or after a major change to your one line. So, your distribution system, and, the major change is a kind of a gray area. So really our recommendation is, if you're going to do any kind of upgrades, if you're going to add process line, or you're going to add, to your facility, you should be doing arc flash study in conjunction with that equipment upgrade or change to the process. There is also, I guess, to add to that, there is some, there are certain insurance providers that require more frequent than what OSHA prescribes.
Okay, there's one more question that maybe we didn't answer. This is going to be an interesting one. Do the 3 major arc flash software packages have the old and new 2018 standard as selectable options, and therefore the ability to run a comparison?
So the answer there is yes. You said 3. The 3 that come to my mind would be ETAP, SCAM, Easy Power. Those all have selectable options between the 2002 version and the 2018 version.
Okay, a couple more questions came in. How do we get more information on UFIS? We will certainly send that out to you. Here's one. What do you typically do for panel boards that have a molded case circuit breaker that is dangerous on the line side, but not on the load side? How do you label it? And go ahead, Tony.
Yeah, so that's a good one. Typically, in a panel board, you're going to label the entire piece of equipment based on that line side calculation, because you don't know where that fault is going to happen, and there's no electrical isolation between the main and the feeders or branch circuits in that panel. So you would label that entire piece of equipment based on that line side calculation. That's pretty standard. Even if you do have a fault in the busing or one of the feeder circuits, you don't know that it couldn't arc over to the line side of the main anyways. So that would be the typical practice there.
Here's a good question. NFPA 70E Article 130.5F states, the results of an incident energy analysis to specify an arc flash PPE category in Table 130.7C 15C shall not be permitted. We have always seen the 4, 8, 25, and 40 table used. Wondering why the wording, this wording is here. you have any comments on that? Have you studied that section of the NFPA?
Yeah, that one seemed a little wordy to me. Maybe if that one's done in like an email format, I can dissect it and dive into that one a little more. I'm not sure I'm following all of the different article references, so I need to look more into that one.
Okay, fantastic. Well, last poll question. If you can rate our performance. And after that, we're going to say, we're going to conclude and say thank you for attending and thank you for the questions. And we've got a whole list of, well, here's another question. All right. On motor control centers with molded case circuit breaker and arms. I guess that's, okay, I'm not familiar with that acronym, arc resistant.
ARMS?
Anyway. Yeah.
Arc reduction maintenance switch would be what I think that's
Maintenance switch.
Oh, arc reducing maintenance switch. Okay, got it. All right.
Yeah, that's what it is, Michael.
Says on motor control centers with molded case breakers and the arc reducing maintenance switch, we labeled line and load with and without the arc resistant maintenance switch. We do not label individual buckets. We go with worst case results with maximum and minimum short circuit data from utility as well as their different switching modes. Okay, is there a question there?
Michael, I think they're stating what they do is, it sounds like there's an upstream arms device feeding an MCC. And answer the question, yes, we've seen that where there's two ratings on the motor control center bus rather than the buckets. I see that quite often where there's one rating with arms, one rating without arms.
Okay, fantastic.
Josh, you agree with that? I would assume.
Yeah, just make sure that that maintenance switch is on the feeder breaker feeding that MCC and not on the main. If it's on the main, you want to be careful about using that reduced rating if you're working in the main section, because then that value wouldn't apply. So just keep in mind where that switch, what piece of equipment that switch is on when you're applying that label value.
Great. Well, thank you guys, all the panelists that participated. Thank you to the attendees for all the questions, and we look forward to seeing you at the next webinar. You will receive a certificate within 24 hours, or I believe actually by tomorrow, 5 p.m. If you do not receive a certificate, please email us. Thanks again.
Thank you, everyone.
Thanks, everybody.
Thank you.